Let's say that you're an event organizer planning your freestyle battle tournament. You've watched other events to learn from what they've done, and you've seen this happen. One judge votes for one dancer, while the rest vote for a tie. And it just feels incomplete, doesn't it? Shouldn't that be a tie since the majority of the judges voted for a tie? Well, what you're thinking of is something that's rare to see in dance battles: plurality tie votes. Typically in dance battles, the dancer with more votes is the winner. The only time a tie occurs is when the number of votes for the dancer on the left is the same as the number of votes for the dancer on the right. Tie votes in this system are where judges are choosing to abstain from picking a winner. With plurality tie votes are now active decisions where the judge is voting for a tiebreaker to happen. If there are more tie votes than there are votes to either dancer, then the battle will go into a tiebreaker. When I say it's rare, I mean it's rare. Out of the many dance battle events I've been to, I've only seen it used once. In my previous video, I showed an example where 3 judges using left-right tie votes had 27 different possible voting configurations. 10 of those configurations had the dancer on the left winning, 10 of them had the dancer on the right winning, and 7 of them were a tie. With plurality tie votes, 6 of those configurations are now counted as ties because most of the judges voted for a tiebreaker. 48% of the possible voting configurations are now ties in this system. Okay, cool. Time to break out the math to see how this new system changes things. We need to be a bit more careful when counting up the possible voting configurations. That little trick with Pascal's triangle won't work here. Let's step it up and use the multinomial theorem. This equation allows us to calculate the number of voting configurations with a certain outcome. In this equation, J is the number of judges present, L is the number of left votes, R is the number of right votes, X is the number of tie votes, and the exclamation mark means that we're taking the factorial of each of those numbers. Here's an example. Let's say we have 3 judges, and all 3 of them vote for the left. J would be 3, L would be 3, R would be 0, and X would be 0. Plugging all this into a calculator gets us 1 configuration, which makes sense. There's only one way to have all 3 judges vote for the left. How about another example? Let's say we still have our 3 judges, 2 of them vote for the right, and 1 votes for a tie. Well, in this case, J would be 3, L would be 0, R would be 2, and X would be 1. Plugging all this into a calculator gets us 3 configurations, which is what we saw earlier as well. We have our equation to count configurations. Now we have to think about the conditions for ties to occur. One condition that always applies: the total number of votes must be the same as the number of judges. Makes sense, right? So we can express the number of ties like this and use it in our equation. If we set the number of votes to the left to be the same number of votes to the right, we end up with our original tie configurations. Example: with 5 judges, there's 3 combinations to have left and right votes equaling each other. Plugging all these into the equation and adding them all up gets us 51 tie configurations, which is what we got last time. To get the new set of possible tie configurations with plurality tie votes, we have a different set of conditions. The number of tie votes needs to be greater than the number of left votes, the number of tie votes needs to be greater than the number of right votes, and the number of left votes cannot equal the number of right votes. That last condition is so that we don't double count the original tie configurations. Going back to our 5-judge example, there are now 4 more combinations that yield ties. Plugging all this into the equation and adding them all up gets us 30 new tie configurations. Okay, you ready for the big reveal? Because you know I already did the calculations to get the new tie configurations and graph the results. You sure you're ready to see? Well, here it is! Just like in the last video, the horizontal axis is the number of judges present, and purple is a tie percent from our original tie conditions. The magenta on top is the added tie percent when accounting for plurality tie vote conditions. And this is just weird. Like, you can see that somehow the total tie percent adds up to 33.3% most of the time, except for those weird spikes that happen. Like, what the heck is going on? Well, if we go back to when we calculated tie percent just using left-right voting, we saw that there were spikes when the number of judges was a multiple of 2. At all other points, it was an even split between the 2 possible outcomes. For the new left-right tie voting, there's spikes when the number of judges is a multiple of 3. At all other points, it's an even split between the 3 possible outcomes. At least that's how I understand it. I can't think of any other ways to explain why this happens, and also, I don't think this is something that's typical either. Anyway, you now have a little bit of forbidden knowledge. If you truly want to maximize the amount of tiebreakers in your bracket, have 3 judges use left-right tie voting and use the plurality tie condition. But that's probably why plurality tie votes are not a common thing to see. Listen, I know I said I like seeing tiebreakers in the last video, but there's a limit on that. 1 or 2 tiebreakers is fine, but not a third of your bracket ending in ties. Anyway, thank you so much for watching, and I'll see ya in the next video. Oh, and one last thing. Notice how on this graph, the tie percent for 4 judges is still less than the tie percent for 3 judges. Yep, it's still valid to have 4 judges.